We're going to spend the next half hour working various kinds of mole problems that students are almost certainly going to be asked to solve in most traditional high school chemistry classes. I'm assuming that you have pretty well mastered the material that was covered in the previous lecture as well as lectures number 2 and 3. If that's not the case, I strongly suggest that you go back and go through these lectures again, as they provide the firm foundation upon which your problem-solving skills are going to be based. We have several purposes today. One, obviously, is that you become proficient at solving mole problems, because the mole concept is an extremely important concept, and it's going to come up again and again throughout the entire course. In addition, working mole problems will provide us with an excellent opportunity to sharpen and even further refine your ability to reason quantitatively and to develop a good understanding of the fundamental quantities that we're dealing with when we solve these kinds of problems. In mole problems, there are 3 quantities that are typically encountered: grams, moles, and molecules. Hopefully, you have a good feeling for what each of these things is. I mean, if you've held objects in your hand and tried to estimate their mass, as we recommend in Lecture 4, you should have a pretty solid understanding of what we mean when we say something has a mass of, let's say, 35.4 grams or whatever. After the last lecture, I hope you have at least a fairly good idea of what we mean when we talk about a mole of something. And molecules, of course, are those little, extremely small particles that things are made of. And this term also includes atoms and what we call formula units. In lecture number 2, we talked about 2 kinds of numbers: amounts and this per that's. Grams, moles, and molecules are all amounts. Amounts of a substance in grams, amounts of a substance in moles, or amounts of a substance in molecules. Now, what kind of this per that's might you encounter in mole problems? There's basically only 2. There's what we call the molar mass of a substance, expressed in units of grams per mole. It might be written this way, but more commonly it's written this way. This tells us what a mole of something weighs. The other this per that is what we call molecules per mole. How many molecules are contained in 1 mole? Now, in working all mole problems, there are 2 absolutely key ideas. All moles contain the same number of particles, 6.02 times 10 to the 23rd. There are 6.02 times 10 to the 23rd molecules per mole for anything, just like all dozens contain 12. Written with the proper units, that becomes 6.02 times 10 to the 23rd molecules per mole for anything. It doesn't matter what it is. The other key idea is that moles of different substances will have different masses, because some molecules are heavier than others. To help you visualize this, I brought a mole of different substances into the studio. These have actually been measured out quite carefully. Here I have moles of 7 different substances. I've actually arranged them in order of increasing mass. The first substance is actually water. I've added some green dye to it, vegetable dye, just so you could see it. It's hard to see a colorless liquid on camera. Water has a molar mass of 18 grams per mole. This is aluminum. Molar mass is 27. This happens to be methanol, which is also colorless, but which I've put some vegetable dye in. Its molar mass is 32. This is common ordinary table salt, sodium chloride, molar mass 58.5. This is copper, pure copper, molar mass 63.5. This is a chemical called copper sulfate pentahydrate, to be technical, and its molar mass is 249.6. And the last beaker contains sucrose, common ordinary table sugar. Its molar mass is 342. Now, as you looked at the mole of these different substances, you probably made some observations. First, you probably noticed that they took up different amounts of space. The moles had different volumes. We would assume that this is because the molecules, atoms, or formula units of some of these substances are either larger or smaller than the molecules, atoms, or formula units of the other substances. In addition, we wrote down the molar masses of the substances, how much a mole of each of them weighed. We noticed that different moles had different masses. For example, the heaviest mole was sucrose, and the lightest was water. And we know that that's because a molecule of sucrose happens to be much heavier than a molecule of water. And while you certainly can't observe this, your mind should be telling you that this very important fact, even though all those moles took up different amounts of space, and even though all those moles had different masses, they all shared one thing in common. They all contained 6.02 times 10 to the 23rd molecules, atoms, or formula units. Now, when you work mole problems, it's important that you visualize a mole of whatever is given in the problem in your mind. It would be nice, if you could put a mole of the substance on the table in front of you as you work the problem, but since you obviously can't do that, you may have to draw little pictures. And the pictures I suggest you draw might look something like this. How would you visualize a mole of, let's say, water and sucrose? On the screen, we've drawn a visual representation of a mole of water and a mole of sucrose. Now, if you're a very critical thinker, you might say, you've drawn these pictures incorrectly, because sucrose might take up more space. You should have drawn the circles different sizes. You're right. But I have no way of knowing when I'm working a problem how much space a mole of something would take up. Believe it or not, just because substance A might have a greater molar mass than substance B doesn't necessarily mean that it would take up more space. Since I lack this information, all I can really do is draw some arbitrary sized circles. It turns out not to be important anyway, because we almost never would have a problem in which the volume taken up by a solid or a liquid would have anything to do with the problem. A mole of water weighs 18.0 grams, whereas a mole of sucrose weighs 342.0 grams. Inside each of these moles, there are some dots. There are the same number of dots in each circle. You'll have to trust me on that one. I actually haven't counted them either. And while I obviously couldn't have drawn all the dots, that would take forever. There's 6.02 times 10 to the 23rd dots in each circle. Those dots represent the number of molecules. Now, I'm often asked by students, do I really have to draw these pictures? The honest answer to that question is, I don't know. Many students have no difficulty whatsoever visualizing all of this in their minds. They don't need the pictures. Some students absolutely need to draw the pictures and think about them. Everybody's different. It depends on how well you really understand these concepts and can visualize them mentally. If you need to draw the pictures, then do it. If you don't. Only you know if this is necessary. But if you are in doubt, draw. So let's say that when you're given a mole problem, at least early on, draw these pictures and think about what they represent. A mole of water, a mole of sucrose. Both contain the same number of molecules. They both had the same number of dots. But the mass, the weight of these two samples is different. And once again, that's because a sucrose molecule is much heavier than a water molecule. In this example, it's kind of easy to see why. Sucrose molecules contain so many more atoms than a water molecule. And when these problems are presented to you, I strongly suggest that you approach these problems, indeed all problems, in the following way. Read the problem several times if necessary. If you can solve it right away, that's great. Then just go ahead and solve it. But again, early on, if you aren't immediately certain as to how to go about solving that problem, read it several times. Think carefully about what the problem is saying, and perhaps even draw a picture or pictures of the quantities represented in the problem. And be certain to always attach the proper units to all numbers given in the problem. Only rarely on certain kinds of problems do we leave off the units. Certainly at this stage of the course, you shouldn't ever be writing down numbers without attaching the proper units. Don't write down 18. Write down 18.0 grams per mole. Don't write down 6.02 times 10 to the 23rd. Write down 6.02 times 10 to the 23rd molecules per mole. Then see if you can put the quantities together in what we might call the natural logical way. as you did with the students in rooms problem, and hopefully as you did with the density problems. Once you've decided how to put the numbers together, whether the logical thing is to multiply them or divide them, and if you divide them, which number goes in the numerator and which in the denominator, then take out your calculator and calculate. Calculate the actual numerical answer to the problem. Write it down in what might be called a reasonable way. Don't copy all the digits off your calculator, but don't round off too drastically either. Finally, attach the correct units to the answer, and then, if possible, judge how reasonable your answer is. Sometimes that's going to be easy to do and sometimes not so easy, but try. See if the answer seems to make sense. If you feel a little shaky, then check your answer using the factor label approach or the proportion approach or formula approach. Well, hopefully you'll feel confident enough that you won't feel these approaches are necessary. Only then should you restart the DVD and watch the solution. If you missed the problem, come back and try it again after a while when you no longer remember how it was solved. So let's take a look at the first problem. How many moles of water, H2O, are contained in 5.87 grams of water? Now the problem says that you have 5.87 grams of water, and you're supposed to find out how many moles are contained in that sample. Now, what would I need to know in order to do that? Well, if I'm only given a number of grams, but I'm asked for the number of moles, I can only do that if I know the number of grams you need to have 1 mole of water. Well, that's the molar mass. We've already done this several times, so I haven't bothered to do it again. Water weighs 18 grams per mole. This tells me that I would need 18.0 grams of water in order to have a whole mole. Since you only have 5.87 grams, you should now realize that you have to have less than 1 mole of water. You only have a fraction of a mole. Now, the problem didn't specifically ask whether you had more or less than 1 mole, but this is the kind of thinking habit that you should be getting into. When you see 5.87 grams and 18 grams per mole, you should look at those numbers and almost immediately realize that you have less than 1 mole. But the problem wanted you to calculate the actual number of moles, so you have to do the arithmetic. This is the classic Gazinta problem. I have an amount, 5.87 grams, and I have a this per that, 18 grams per mole. 5.87 grams divided by 18 grams per mole means that I have about 0.326 moles of water. I mean, if you wrote the answer down as 0.33 or even carried 1 or 2 more decimal places, I mean, that's okay. The only important thing is that you realize that the correct way to solve this problem was to divide the 5.87 by the 18.0. To multiply the numbers or divide 18.0 by 5.87 just wouldn't make any sense, because you know that you have to have less than 1 mole of water. So let's try another. How many moles of sucrose are contained in 5.87 grams of sucrose? You notice that in this problem I gave you the same mass as in the last problem, but in no way does this mean that you have the same number of moles. Sucrose has a different molar mass than water. The molar mass of sucrose is 342.0 grams per mole, quite different from the value for water. We went over this molar mass calculation in the last lecture, and it is shown once again on the screen. Since the molar masses of sucrose and water are different, 5.87 grams of sucrose is not going to contain the same number of moles as 5.87 grams of water. It's going to be a much smaller fraction of a mole. I mean, if someone wanted to give you a mole of sucrose for a present, they'd have to give you 342 grams. They only gave you 5.87 grams, cheapskates, so they only gave you a small fraction of a mole. Mathematically, this comes out to be about 0.0172 moles, as you can see. And another. How many moles of carbon dioxide, CO2, are there in a sample of carbon dioxide with a mass of 68.2 grams? Once again, we are given the number of grams of something, in this case carbon dioxide, and we're asked to find the number of moles. We can only do this if we know the number of grams there would be in 1 mole. This, of course, is the molar mass. So we need to calculate the molar mass of carbon dioxide. This calculation is shown on the screen. Carbon dioxide weighs 44.0 grams per mole. But we don't have 44.0 grams. We have 68.2 grams. Now, 68.2 is more than 44. So now you should immediately realize that in this case, you have more than 1 mole. Specifically, we have 68.2 grams divided by 44 grams per mole, or a total of about 1.55 moles of CO2. This problem was really just like the last two previous problems, except that you ended up with more than a mole instead of less than a mole. But the reasoning was the same. So let's try another. How many grams of water are contained in 6.33 moles of water? Now, this is kind of a key problem. If you get this problem correct, I think you're zeroing in on having a real good idea of what the mole concept is all about. In addition, you're keying in on the simple quantitative reasoning that allows you to quickly see how to obtain the correct answer. This problem is a little different from the previous problems. Instead of being given the grams and being asked to find the number of moles, this time we were given the number of moles and asked to find the number of grams. But once again, we can only do this if we know how many grams there are in a mole, which of course for water is 18 grams per mole. Now, in the first three problems, we divided to get the answer. But in this problem, you don't divide, you multiply. Now, what would lead you to the conclusion that you should multiply the numbers? The answer is a good understanding of what the numbers in the problem really represent. I have drawn here a representation of a mole of water. A mole of water weighs 18 grams. The molar mass of water is 18 grams per mole. This means that if someone were to give you 1 mole of water for a present, they would give you 18 grams of water. But this person is very generous. He gave you not 1 mole, but more than 6 moles, 6.33 to be exact. 1 mole of water weighs 18 grams. That's what the molar mass tells us. Now let me ask you a question. If 1 mole of water weighs 18 grams, what do you think 2 moles would weigh? How about 3 moles? 4? 5? 6? 6.33 moles? What I'm hoping is that you realize that if 1 mole weighs 18 grams, then 2 moles is going to weigh twice as much. 3 moles, 3 times as much. 4 moles, 4 times as much. 5 moles, 5 times as much. 6 moles, 6 times as much. And 6.33 moles, just 6.33 times as much. So to get the answer, you just multiply 6.33 moles times 18 grams per mole to give you a final answer of something around 144 grams. And another. If you had 2.33 moles of nitric acid, HNO3, how many grams of nitric acid would you have? Well, nitric acid weighs 63 grams per mole, as shown on the screen, so 1 mole of nitric acid would weigh 63 grams. And now you just apply the same logic. If 1 mole weighs 63 grams, then 2 moles would weigh twice as much. And 2.33 moles would weigh just 2.33 times as much, which comes out to be 2.33 moles times 63 grams per mole for a total of about 147 grams. Notice that even though our picture included a lot of dots representing molecules, we didn't need to do anything with molecules when we solved this problem, because nowhere in the problem was anything given or asked about molecules. And another. How many grams of sulfuric acid, H2SO4, are contained in 0.373 moles of H2SO4? I hope that you recognize that this problem is very similar to the previous two. The only difference is that in this problem you have less than 1 mole rather than several moles. But that doesn't change the logic. Sulfuric acid weighs 98.1 grams per mole, as shown on the screen. So if we had 1 mole of sulfuric acid, we would have 98.1 grams of sulfuric acid. But we don't have a whole mole. We only have a fraction of a mole. Therefore, we're only going to have a fraction of 98.1 grams. Specifically, if we have 0.373 of a mole, or 0.373 of 98.1, that comes out to be about 36.6 grams of sulfuric acid. And another, how many moles of water are contained in a sample of water that contains 4.55 times 10 to the 23rd molecules of water? Now, this problem is a bit different, so think about it carefully before you try to solve it. Now, if you're like many students, you may have begun this problem by calculating the molar mass of water. I mean, after all, that's what we did in all the previous problems. It turns out that that's not needed in this problem. Now, how would you know that? Well, the problem is giving you a certain number of molecules and asking you to find the number of moles. There is absolutely nothing in this problem that deals with the mass. No one gave you a mass in grams. No one asked you for a mass in grams. So there is absolutely no need to put grams into this problem. All I need to know is simply, how many molecules are there in 1 mole? In a mole of water, indeed, in a mole of anything, there's 6.02 times 10 to the 23rd molecules. If you had a mole of water in your hand, you would be holding 6.02 times 10 to the 23rd molecules. Well, you don't have that many molecules, so you don't have exactly 1 mole. You have 4.55 times 10 to the 23rd molecules. Now, if your mental mathematics is pretty good, you may even be able to compare these two numbers in your head and realize that you have a little less than 1 mole. 4.55 times 10 to the 23rd molecules divided by 6.02 times 10 to the 23rd molecules per mole means that we have about 0.756 moles of water. And another, how many molecules are contained in 7.25 moles of C6H12O6, which happen to be glucose? Now, this problem is both similar and different from the last problem. It is similar in the fact that, once again, the problem doesn't give or ask anything about grams. So there's no need to calculate the molar mass of glucose, C6H12O6. But it's different because in this problem, you have to multiply the numbers given in the problem instead of dividing them. And the logic that allows you to see this runs as follows. You know that there are 6.02 times 10 to the 23rd molecules in 1 mole. So thinking logically, we know that if we had 2 moles, there would be twice as many molecules. 3 moles, 3 times as many. And 7.25 moles would contain 7.25 times as many. It's just as simple as that. 7.25 moles times 6.02 times 10 to the 23rd molecules per mole means that I have about 4.36 times 10 to the 24th molecules. And yet another. What is the mass of a sample of sodium chloride, NaCl, that contains 5.69 times 10 to the 22nd formula units of sodium chloride? This is truly a key problem. If you solve this kind of problem correctly on the first try, it is a strong indication that you probably understand the mole concept quite well. If you didn't, don't feel bad. You have plenty of company. Just keep on working, or more importantly, thinking, because it will come in time. Even though this problem deals with what are called formula units, we can treat these as if they were the same thing as molecules. Just as there are 6.02 times 10 to 23rd molecules per mole, there are 6.02 times 10 to 23rd formula units per mole. In fact, I'm just going to call these molecules for the time being, since I think it makes the problem a bit easier to visualize. We are given the number of molecules of NaCl and asked to find the number of grams of NaCl. Since this problem is asking for grams, I know I'm going to need the molar mass of NaCl. So let's calculate that. As shown on the screen, that comes out to be 58.5 grams per mole. Now, it would have been nice if they had told me the number of moles of NaCl that I had. Then I could have just multiplied the number of moles times the number of grams per mole, and I'd have the answer. But they didn't give me the number of moles. Instead, they gave me the number of formula units, or which I'm calling molecules. But I really need the number of moles. Is there any way I can take the number of molecules they gave me, 5.69 times 10 to the 22nd molecules, and change that into moles? Definitely. I know that there are 6.02 times 10 to the 23rd molecules in 1 mole. And I have 5.69 times 10 to the 22nd molecules. Comparing these two numbers shows me that I have less than a mole of sodium chloride, because 5.69 times 10 to the 22nd is less than 6.02 times 10 to the 23rd. Specifically, I have 5.69 times 10 to the 22nd molecules, or formula units in this case, divided by 6.02 times 10 to the 23rd formula units per mole, meaning that I was given about 0.0945 moles of sodium chloride. 9.45 times 10 to the minus second moles if you write it in scientific notation. Now, I just need to see what this fraction of a mole weighs. To find that, I just need to take that fraction of 58.5 grams. The word of, by the way, is almost always a clue to multiply. Don't let the numbers mess up your thinking. If you had half of a mole, then I'll bet you would know to take half, or 0.5 of 58.5. You would know that you should multiply the numbers. If you had a tenth of a mole, you would have multiplied 0.1 times 58.5. Well, just because you have 9.45 times 10 to the minus second of a mole doesn't change the logic. You just take 9.45 times 10 to the minus second of 58.5. And you find that you have about 5.53 grams of sodium chloride. And the final problem, and before you work this, think very carefully about what this question is actually asking. What is the mass of 1 molecule of water in grams? I think this problem is especially useful and interesting to think about. When students are first asked this question, one of the most common responses is, "Wow, that's easy, I know how to do that." And then they quickly respond that the answer is 18 grams. What? 1 molecule of water weighs 18 grams? A whole nickel only weighs about 5 grams. A whole nickel! I can't even see a molecule of water. It couldn't possibly weigh 18 grams. That just doesn't make any sense. There must be something more to this problem. And there is. 1 molecule of water doesn't weigh 18 grams. A mole of water weighs 18 grams. And a mole of water contains 6.02 times 10 to the 23rd molecules of water. So 6.02 times 10 to the 23rd molecules of water weigh 18 grams. So what would 1 molecule weigh? To find that out, just take the weight of all the molecules, 18 grams, and divide by how many molecules you have, 6.02 times 10 to the 23rd. Remember, anytime you divide two numbers, you are making the denominator 1. Taking the weight of all the water molecules, 18 grams, and dividing by the number of molecules, 6.02 times 10 to the 23rd, tells me that each molecule of water has a weight of about 2.99 times 10 to the minus 23rd grams. Is this a reasonable answer? Well, it certainly isn't unreasonable. I mean, 1 molecule of anything should weigh almost nothing, and 2.99 times 10 to the minus 23rd is certainly almost nothing. I mean, I don't know if this answer is correct, but it certainly appears to be reasonable. At this point, there are a number of possibilities. You may be finding these problems immensely easy, almost boring, hopefully. If so, that's great. You may feel that you kind of understand this, but you're a little shaky. That would be the most common thing. What you need is a lot more practice, solving a lot more problems. And these can probably be found in your textbook that you might be using, at least if it's a traditional text, and or the workbook that accompanies this course. The third possibility is that you are still confused. If that's the case, then you need to go back to this lecture again and possibly some of the previous lectures. Students often ask me, how long should I study this? That's an easy question to answer, as long as it takes, whether that's 1 minute or many hours. In the next lecture, we're going to introduce another variable into this mix, and we'll see how the addition of another variable affects how we solve problems.